Have you ever found yourself standing at a crossroads in your life, haunted by the question, what if? What if you had taken that other job? What if you had boarded that train instead of missing it? We usually dismiss these thoughts as simple tricks of the imagination, ghosts of a future that never happened. We tell ourselves that life is a single, straight road, and the past is set in stone. But there is a massive difference between how you feel the world works and how it actually works. We assume that when we make a choice, the other options vanish, but physics suggests that the universe is not a movie editor that cuts out the scenes you didn't pick. It keeps the footage. It implies that the version of you who got on that train is not a ghost inside your head. They are real. They are breathing, they are thinking, and they are living that alternative life right now, separated from you by a thin wall you cannot see. Tonight, we are going to break down that wall and show you exactly where all those other versions of you are hiding. To find these other versions, we first have to answer a simple question. If the universe is keeping the footage of our other lives, why can't we see it? Why does our world look so singular and solid? The answer is that human perception is not a perfect camera. It is a filter designed for survival, not for truth. Think about a ceiling fan spinning at full speed above your head. When you look at it, you do not see three individual solid blades. You see a transparent, blurry disc. Your eyes and your brain cannot process the fast movement, so they average the reality into a simple, static image. You know the blades are there, but your perception merges them into a single object to keep things simple. Theoretical physics suggests that our experience of a single timeline is exactly like that blurry disk. At the fundamental level, the particles that make up your body, electrons, quarks, photons, do not have a fixed solid position like a rock sitting on the ground. Until they interact with something, they exist in a state called superposition. This means an electron is not at point A or point B. It is in a state of potential where it occupies both A and B simultaneously, acting more like a rippling wave on a pond than a solid marble. But here is the question that keeps physicists awake at night. Where exactly is the line between the quantum world and the human world? At what point does the magic stop? We tend to assume there is a boundary where the weird rules of atoms disappear and the normal rules of people begin. But nature doesn't have boundaries. There is no magical fence where physics changes. Since you are nothing more than a massive collection of these quantum particles, logically, the collection should behave exactly like its parts. The reason you don't feel like you are splitting into multiple versions is the same reason you don't see the individual blades of the fan. You are living inside the blur. We are trapped in a specific perspective that forces us to see only one sharp, consistent outcome, while the actual reality is a massive, spinning superposition of all possible events happening together. To fully grasp why physicists are so confident that reality is splitting around you, we have to look at the experiment that started this entire headache. It is known as the Double Slit Experiment, and it remains the single most famous demonstration of how the universe breaks our common sense. Imagine for a moment that you are holding a tennis ball in your hand and facing a wall with two open windows. If you throw the ball, logic dictates that it must pass through either the left window or the right window. It cannot physically go through both at the same time. If you threw 1,000 balls, you would eventually see two piles of them on the ground behind the wall, one pile behind the left window and one pile behind the right. This is how the world works for big, solid objects like us. But in 1927, when scientists tried this exact same test with electrons, something impossible happened. They fired individual electrons at a barrier with two tiny slits, expecting them to behave like miniature tennis balls. But when they looked at the detector screen behind the barrier, they did not see two piles. Instead, they saw a complex pattern of many vertical stripes, known as an interference pattern. This is the kind of pattern you would get if you pushed two waves of water through the slits. The waves would ripple out, overlap, and crash into each other, creating a series of peaks and valleys. But here is the mystery that defies logic. The scientists were firing the electrons one by one. There was no other electron for the first one to crash into. So, how could a single particle create a wave pattern? What was it crashing into? The only mathematical explanation is that the single electron did not choose a path. It effectively split into a ghost wave, went through the left slit and the right slit simultaneously, interfered with itself on the other side, and then hit the wall. This experiment proves that at its core, matter is not solid. It is a wave of possibilities. But this leads to an even stranger discovery. When the scientists got suspicious and placed a sensor at the slits to secretly watch which hole the electron actually went through, the behavior stopped. The moment they watched it, the electron stopped acting like a wave and went back to acting like a solid tennis ball, going through only one slit. It was as if the particle knew it was being watched and decided to hide its true nature. This forces us to ask a terrifying question. Does the universe only look solid because you were looking at it? And if you stopped looking, would the chair you are sitting on dissolve back into a wave of infinite possibilities? For decades, the smartest minds in physics tried to sweep this problem under the rug. In the 1920s, the legendary physicist Niels Bohr and his colleagues developed what is called the Copenhagen interpretation. They argued that when you measure a particle, you force it to choose. They claimed that the wave of possibilities simply collapses into one single reality, and all the other possibilities just vanish into thin air. It was a convenient explanation because it saved our intuitive view of the world. It told us that even though atoms are weird, the world we live in is safe and singular. It told us that the other versions of the electron simply disappear. But there was a problem. The mathematics of quantum mechanics never actually described this collapse. The equations did not say the other possibilities vanished. They just said they became separated. Then, in 1957, a young doctoral student at Princeton University named Hugh Everett III decided to take the math literally. He looked at the equations and asked a simple, dangerous question. What if the wave never collapses? What if the electron does not choose one slit or the other, but actually does both, and the universe splits to accommodate both outcomes? Everett argued that when you measure the particle, the universe branches into two separate, non-communicating layers of reality. In one layer, you see the electron go left. In the other layer, an identical version of you sees the electron go right. This was the birth of the many worlds interpretation. It suggests that reality is like a radio signal that is constantly splitting into different frequencies. Just because you are tuned into one frequency does not mean the others have stopped broadcasting. Everett showed that the collapse was a myth we invented to make ourselves feel better about living in a singular world. But if he was right, it means that nature never destroys information. It means that every time a quantum event has multiple possible outcomes, all of them happen. Think about what this implies for the history of our world. How many times has a tiny quantum event shifted the course of history, creating a branch where things went terribly wrong or wonderfully right? And if the math is correct, why do we treat this as science fiction instead of historical fact? The most common objection to this idea is that it applies only to the subatomic world. You might look at your hands and say that you are not an electron, so you do not split. But this objection fails when you trace the chain reaction of an observation. Let us imagine a single radioactive atom that has a 50% chance of decaying and releasing a poison, and a 50% chance of remaining stable. This is the famous setup of Schrödinger's cat. The atom is in a superposition of decaying and not decaying. But the atom is not isolated. It interacts with the detector machine. According to the laws of physics, when a quantum particle interacts with a larger system, that larger system becomes entangled with it. The detector enters a superposition of having detected radiation and having detected nothing. Then the signal travels to the poison vial. The vial enters a superposition of being broken and remaining whole. Then the poison travels to the cat. The cat enters a superposition of being alive and being dead. And finally, you open the box. The light from the cat hits your retina, travels up your optic nerve, and fires neurons in your brain. There is no physical barrier that stops the spread of this split. The superposition infects everything it touches. The moment you look at the result, you become part of the equation. Your brain physically enters two distinct states. In one branch of reality, your neurons record a living cat. In another branch, they record a dead cat. Both versions of you are equally real, and both versions feel like they are the only one. This is the mechanism of the multiverse. It is not about traveling to distant dimensions. It is about the constant branching of the here and now. Every time a neuron in your brain fires, a process driven by the movement of ions and electrons, the universe accommodates the alternative. This means that your consciousness is constantly fracturing across the probability space. If you are reading this sentence right now, there is a version of you who got distracted and clicked away 5 seconds ago. That version is just as real as you are, but you can never speak to them again. So if you're constantly splitting, who is the real you? Are you the trunk of the tree, or are you just one distinct leaf unaware of the forest around you? You might be listening to this and thinking that this is all just a beautiful philosophical game. You might be telling yourself that parallel worlds are just a convenient way to explain math on a blackboard, but they have no impact on the real world of steel and silicon. But that skepticism runs into a wall when we look at the technology that is currently sitting in laboratories at Google and IBM. I am talking about quantum computers. These machines are not just faster versions of the laptop on your desk. They operate on a fundamentally different logic that practically forces us to accept the existence of parallel realities. To understand why, we have to look at how a normal computer works. Your smartphone processes information in bits, which are like tiny switches that can be either on or off, representing a 0 or a 1. It creates a single, linear string of calculation. But a quantum computer uses qubits. A qubit is a particle, like an electron, held in a magnetic trap. Because of superposition, this qubit can represent a 0 and a 1 at the exact same time. If you link enough of these qubits together, the machine can perform millions of calculations simultaneously, rather than one after another. The pioneer of quantum computing, the Oxford physicist David Deutsch, posed a challenge that has never been satisfactorily answered by skeptics. He asked us to imagine a quantum computer factoring a number with more digits than there are atoms in the visible universe. When the computer spits out the correct answer, it has performed more distinct calculations than there are particles in the cosmos to do the counting. So, where were those calculations performed? If the visible universe does not have enough resources to hold the scratch pad for that math, then the computer must be utilizing resources from somewhere else. Deutsch argues that the only logical explanation is that the computer is distributing the workload across parallel versions of itself in other timelines. It is collaborating with its own shadow copies. When we run a quantum algorithm, we are effectively outsourcing our homework to the multiverse and then collecting the answer. If parallel worlds do not exist, then how can a machine perform a task that requires more computing power than exists in our entire reality? Are we ready to accept that our most advanced technology is actually an interdimensional device? The fact that these computers work is the strongest physical evidence we have that the walls of our reality are porous. This brings us to the end of the first level of our journey, and it forces us to completely rewrite the biography of your life. We started by asking, what if? Treating it as a question of regret. But quantum mechanics transforms that question into a statement of fact. The many worlds interpretation tells us that you are not a single person moving through a single story. You are a multiplicity. You are a sprawling bush of events that is constantly growing new branches. Every time you made a hard choice, you did not actually choose. You simply became the version of you who remembers taking the left path, while another version of you, just as real and just as conscious, remembers taking the right. This realization should not make you feel small. It should make you feel immense. It means that the regret you feel for the things you did not do is misplaced, because in the grand archive of the quantum wave function, you did them. You became the astronaut. You said the words you were too scared to say. You saved the relationship. Those lives are not lost. They are simply running in a parallel operating system that you cannot access from your current desktop. The universe is far too efficient to waste any potential outcome. It captures everything. But if this is happening on the microscopic scale of choices and electrons, does it stop there? We tend to think that the weirdness of quantum mechanics is confined to the tiny world of atoms, while the big world of stars and galaxies follows a simpler set of rules. But what if the entire universe itself is just one bubble in a much larger sea? What if the Big Bang was not the beginning of everything, but just a small pop in a never-ending fireworks display? To understand where the other worlds are hiding, we need to leave the atom behind and look at the edge of the cosmos. If space is infinite, can you truly be unique? When we look up at the night sky, we see a vast dome of stars that seems to go on forever. We call this the universe, with a capital U, implying that it is the one and only total sum of existence. We are taught in school that everything began 13.8 billion years ago with the Big Bang, an explosion that created space and time itself out of nothing. We imagine this event as a singular miracle, a one-off moment of creation that gave birth to the only reality there is. But modern cosmology suggests that this map is laughably incomplete. The picture of a single Big Bang is likely a provincial illusion, similar to how ancient cultures thought their island was the only land in an endless ocean. The new map drawn by physicists suggests that what we call the universe is actually just our local, observable universe. A tiny, illuminated bubble of light, floating in a much darker, much larger ocean called the multiverse. The reason we cannot see beyond our bubble is simple. Light takes time to travel. Since our bubble is only about 14 billion years old, we can only see objects whose light has had enough time to reach us. There is a hard horizon, a cosmic edge beyond which we are blind. But to assume that reality stops at the edge of our vision is as foolish as a sailor assuming the ocean stops at the horizon. If you could fly faster than light, past the most distant galaxy you can see in a telescope, what would you find? Would you hit a wall? Would you find empty nothingness? Or would you find more stars, more galaxies, and perhaps another Big Bang happening right now? The laws of physics suggest that the process that created our world did not stop with us. It is a mechanism that is likely hammering out new universes at this very second. But what is the engine driving this endless creation? To find the engine, we have to go back to 1981, to a late night at the Stanford Linear Accelerator Center. A young physicist named Alan Guth was trying to solve a major problem with the Big Bang theory. The problem was that the universe was too smooth. No matter where we looked, the temperature of the cosmos was almost exactly the same. This shouldn't be possible unless the entire universe had once been in contact to equalize the heat, and then expanded faster than the speed of light to its current size. Guth proposed a radical idea called inflation. He suggested that in the first fraction of a second, gravity effectively reversed. Instead of pulling things together, it pushed everything apart with violent, explosive force. This repulsive gravity stretched the fabric of space-time from the size of a proton to the size of a grapefruit in less than a billionth of a trillionth of a second. It was this rapid stretch that smoothed out the universe. The theory was brilliant, and observation has since confirmed it. But there was a catch that Guth and later the physicist Andre Linde discovered. The math of inflation suggests that once this rapid expansion starts, it is very hard to stop. It is like a ball rolling down an endless hill. In our local patch of the universe, the inflation stopped 13 billion years ago, and the energy of that expansion was converted into the hot matter and radiation that we see as stars and galaxies. We call that moment the Big Bang. But the theory predicts that inflation does not stop everywhere at once. It continues in other parts of the fabric, stretching space further and further forever. This is called eternal inflation. It paints a picture of a universe that is perpetually growing, like a rising loaf of bread. While our little corner of the bread stopped rising and formed a crust, our universe, the rest of the dough keeps expanding, creating new bubbles of stability elsewhere. Does this mean that the Big Bang is not an event in the past, but a process that is happening eternally? The best way to visualize this mind-bending structure is to imagine a giant pot of thick, boiling water. The water represents the highly energetic, rapidly expanding space of the inflationary multiverse. As the water boils, tiny bubbles of steam form within it. Inside these bubbles, the water has stopped boiling. It has transitioned into a gas. In this metaphor, our entire observable universe is just one of those tiny steam bubbles. We are floating inside a pocket of stability where the violent expansion has stopped, allowing stars and planets to form. But outside the walls of our bubble, the water is still boiling. The space between the bubbles is expanding so fast, faster than the speed of light, that the bubbles are being pushed apart from each other forever. This explains why we have never seen these other worlds. We are physically separated from them not by a wall, but by the sheer speed of the expanding space between us. This is the concept of the cosmic foam, or the Swiss cheese multiverse. The cheese is the expanding energy, and the holes are the pocket universes like ours. But here is where it gets personal. If there are other bubbles out there, are they exactly like ours? Or are they strange, hostile wastelands? The theory suggests that when a bubble forms, it traps a specific set of physical laws inside it. It is like rolling a die. In our bubble, the roll gave us an electron with a specific mass and a force of gravity that allows stars to shine. But in the bubble next door, the die might have landed differently. Maybe there, gravity is repulsive. Maybe light does not exist. Maybe atoms cannot bond together. We might be living in a rare Goldilocks bubble, surrounded by an ocean of dead, dark universes where life is physically impossible. But if the dice are rolled an infinite number of times, surely the perfect combination must repeat. To understand why these other universes might look so radically different from ours, we need to ask a question that sounds simple, but is actually quite deep. Why is the electron exactly this heavy? Why is gravity exactly this strong? In our universe, the laws of physics seem perfectly balanced, like a recipe where every ingredient is measured down to the milligram. For decades, scientists hoped they would find a single mathematical formula that explains why these numbers have to be this way. They hoped to find a theory of everything that would prove our universe is the only possible way to build a reality. But string theory, which is currently our best candidate for that master formula, suggests the exact opposite. Developed by pioneers like Edward Witten and Leonard Susskind, string theory proposes that the fundamental particles of matter are not tiny points, but vibrating strands of energy. Just like a violin string can produce different musical notes depending on how it vibrates, these cosmic strings produce different particles, electrons, quarks, photons, depending on their vibration frequency. But here is the catch. The vibration of the string is determined by the shape of the space it is wiggling in. String theory predicts that our universe has extra dimensions, 6 or 7 of them, curled up into tiny invisible knots called Calabi-Yau manifolds. The shape of these knots dictates the music of the strings, and therefore the laws of physics. The problem is that the equations of string theory allow for an almost infinite number of different shapes for these knots. Specifically, there are at least 10 to the power of 500 possible solutions. This is a 1 followed by 500 zeros. This vast collection of possibilities is what physicists call the landscape. Each solution represents a valid, stable universe with its own unique set of physical laws. In the cosmic foam model, each bubble that pops into existence settles into one of these 10 to the power of 500 valleys in the landscape. This means that out there in the foam, there are universes with 10 dimensions. There are universes where light is heavy. There are universes where the strong nuclear force is too weak to hold atoms together. So matter remains a hot soup of radiation forever. If the menu of reality is this large, is it possible that our comfortable, life-filled world is just a statistical anomaly in an ocean of broken, lifeless bubbles? This leads us to one of the most unsettling observations in all of science, known as the anthropic principle. When we look at the constants of nature, the mass of the proton, the strength of gravity, the charge of the electron, we find that they are fine-tuned to an impossible degree of precision. If the force of gravity were just a few percent stronger, stars would burn out in 1,000,000 years, leaving no time for evolution. If it were a few percent weaker, stars and galaxies would never form at all. It feels like we won a cosmic lottery with odds so low, they are practically zero. For a long time, this fine-tuning was used as an argument for a grand designer. It seemed too perfect to be an accident, but the multiverse offers a solution that requires no design, only statistics. Imagine a hotel with infinite rooms. Most of the rooms have no air conditioning, no water, and are filled with toxic gas. Only one room in 1,000,000,000 has a comfortable bed and fresh air. If you wake up in the comfortable room, should you be surprised? Should you assume the manager built the whole hotel just for you? No. You are in the comfortable room because if you were in the toxic room, you would not be alive to ask the question. This is the essence of the anthropic principle. We observe a universe compatible with life, not because the universe loves us, but because we could not possibly observe a universe that wasn't. The vast majority of the bubbles in the cosmic foam are likely barren, dark, and empty. They are failed experiments where the laws of physics did not allow for complexity. We are simply the survivors of a massive process of elimination. We are the winners of a lottery we didn't even know we were playing. But if the hotel is truly infinite, does that mean there are other winning rooms? And more importantly, is there another room exactly like this one, with another guest exactly like you? To answer that, we have to grasp the sheer relentlessness of the inflation mechanism. The theory of eternal inflation does not just say that space is big, it says that space is a factory that never closes. The energy field that drives the expansion, often called the inflaton field, is inherently unstable. It decays into bubbles of stable matter, like ours, but it never decays everywhere at once. The space between the bubbles keeps stretching faster than the bubbles can form. This means the volume of the multiverse is growing exponentially, doubling in size every tiny fraction of a second, forever. It is creating new real estate at a rate that the human mind cannot comprehend. Even if our observable universe is just a finite bubble, the foam it floats in is effectively infinite in volume and eternal in duration. This changes the rules of the game completely. In a finite room, you can count the objects. You can say this is unique, but in an infinite room, the word unique loses its meaning. If you have an infinite amount of space and an infinite amount of time, nature eventually has to repeat itself. It is not a matter of if, it is a matter of when. We tend to think of nature as an artist with endless creativity, constantly inventing new faces, new planets, and new stories. But is nature really infinitely creative? Or is it working with a limited box of paints? If you look closely at the fundamental structure of matter, you realize that the universe is not painting on a blank canvas. It is building with Lego bricks. And if you have a limited number of types of bricks, there are only so many things you can build before you are forced to build the same model twice. This realization brings us to the bridge between the chaotic, diverse bubbles of the multiverse and the eerie, repetitive corridors of the infinite library. Until now, we have been talking about universes with different laws of physics, places where gravity is weird or light is slow. But even if we ignore those strange worlds and focus only on regions that have the exact same laws of physics as ours, we run into a mathematical wall. Let us assume that space goes on forever, and that the laws of physics are the same everywhere. This is the simplest, most conservative assumption in cosmology. It corresponds to what Max Tegmark calls the level 1 multiverse. In this infinite expanse, you don't need exotic string theory to find a parallel world. You just need to travel far enough. The logic is brutal. There's only a finite number of ways to arrange the protons and electrons in a given volume of space. Once you exhaust all those arrangements, you have no choice but to start repeating them. Think of it like a password. If your password must be 4 digits long, there are only 10,000 possible combinations. If you have 10,001 people, 2 of them must have the same password. It is unavoidable. The universe is just a very, very long password made of atoms. And since the universe is infinite, it has an infinite number of users. This leads us to a specific, calculable distance where uniqueness must fail. How far do you have to go before you find a planet that is not just similar to Earth, but is the exact atomic twin of Earth? To visualize this, let's play a game with a standard deck of 52 playing cards. If I ask you to shuffle the deck and lay the cards out in a row, the number of possible orders is massive. It is an 8 followed by 67 zeros. That is a huge number, far larger than the number of seconds since the Big Bang. If you shuffled a deck once every second, you would likely never repeat the same order in your lifetime. It feels like the possibilities are endless, but they are not. They are finite. If you had an infinite line of people, and each person held a shuffled deck of cards, eventually down the line, you would find someone holding a deck that matches yours card for card. Ace of spades first, 2 of hearts second, all the way to the end. It is a mathematical certainty. Now, replace the cards with atoms. The observable universe, the bubble we can see, is just a container. It is about 93 billion light years across. Inside this container, there is a limited amount of quantum slots where particles can exist. Physicists have actually calculated the total number of possible quantum states that can fit inside a volume the size of our universe. It is a number known as the Bekenstein bound, or roughly 10 to the power of 10 to the power of 118. It is a number so large that our human brains cannot handle it. It makes the card deck look like 0. But the crucial point is that it is not infinity. It is a specific number. And if space is infinite, then nature is rolling the dice an infinite number of times. It means that the deck of cards that creates our reality, the arrangement of every star, every planet, every person, and every neuron in your brain must eventually be dealt again. The universe is not an artist. It is a shuffler. And in an infinite casino, every hand gets played eventually. To accept the idea that there is a copy of you out there, you first have to accept a fundamental truth about the texture of reality. We tend to think of space as a smooth, continuous canvas where you can paint any shape you want. We imagine that we can move your hand to the right by ½ an inch, or by a trillionth of an inch, or by an infinitely small fraction of an inch. If space were truly smooth and continuous, then the possibilities for arranging matter would be truly infinite, because you could always shift an atom just a tiny bit more to the right and create a unique state. But quantum mechanics destroys this smoothness. It tells us that the universe is pixelated. There is a smallest possible unit of length, known as the Planck length. It is incredibly small, about 10 to the power of minus 35 meters. You cannot slice space thinner than this. It is the resolution limit of the universe's screen. Because space is made of these discrete, tiny blocks, and because you can only put a particle in one block or another, the number of ways you can arrange the atoms in a given volume is not infinite. It is just very, very large. This logic was formalized by the physicist Jacob Bekenstein. He calculated the maximum amount of information that can be packed into a specific region of space. When we apply this to the size of our observable universe, the giant sphere of galaxies we can see from Earth, we get a hard cap on diversity. The number of possible quantum states for our universe is roughly 10 to the power of 10 to the power of 118. This number represents every possible history, every possible position of every atom, and every possible configuration of light that could exist in a bubble of our size. It is the cosmic equivalent of the odometer on a car. The odometer has a lot of digits, but it is not magic. If you drive long enough, the numbers will run out and the counter will roll over back to 0. The universe is driving down an infinite road of space. Since it only has a limited number of quantum miles, it can display on its dashboard before it runs out of unique combinations. It has no choice but to repeat the cycle. The question is not if the odometer rolls over. The question is, how far do we have to drive before we see the same numbers again? Let us try to visualize the journey to your doppelgänger. We are leaving Earth, flying past the Moon, past Pluto, and leaving the Milky Way galaxy behind. We are traveling through the dark void, passing millions of other galaxies, each with billions of stars. We travel until we reach the edge of what we can see, the cosmic horizon, and then we keep going into the unmapped space beyond. How far do we have to go before the laws of probability force the atoms to assemble into another Earth? Max Tegmark, a cosmologist at MIT, actually crunched the numbers to give us an answer. He calculated that you would have to travel a distance of roughly 10 to the power of 10 to the power of 29 meters. To be clear, this number is a double exponential. It is not a 1 with 29 zeros after it. It is a 1 with 10 billion zeros after it. If you tried to write this number down on a piece of paper, the paper would have to be wider than the entire observable universe just to fit the zeros. It is a distance so vast that it makes the distance to the edge of the galaxy look like a single step. But in the context of an infinite multiverse, this distance is nothing. It is a stone's throw. At that exact distance, statistically speaking, there is a volume of space that looks identical to ours. There is a sun that is the exact same age as ours, down to the nanosecond. There is a planet orbiting it that has the exact same geography as Earth, with the same continents and the same oceans. And on that planet, inside a room that looks exactly like yours, there is a person who has your DNA, your memories, and your scars. They are not just similar to you, they are indistinguishable from you. They remember your first day at school. They remember the taste of the breakfast you ate this morning. Up until this precise second, their life has been a perfect mirror of yours. But here is where the level 1 multiverse gets interesting. The copy doesn't have to stay perfect. Because they are a separate physical entity, their future is unwritten. What happens when the copy makes a move that you don't? Imagine looking through a telescope that could see that far. You focus the lens on that distant Earth, zoom in on your city, and find the window of your duplicate's house. You watch them sitting in the chair just like you. But then, something changes. In your reality, you decide to keep watching this video. But in their reality, a neuron in their brain fires slightly differently due to thermal noise. They decide they are thirsty. They stand up, walk to the kitchen, and pour a glass of water. In that split second, the symmetry is broken. You are no longer identical. You have branched into two distinct variations of the same person. This scenario implies that the infinite library of space doesn't just contain exact copies, it contains every possible variation of you. If you travel further, past the first copy, you will find a version of you who put on a red shirt this morning instead of a blue one. Travel further, and you find a version of you who took that job offer in another city 5 years ago. Travel even further, and you find a version of you who became a professional musician instead of an accountant. This is the ultimate realization of the phrase, everything is possible. In our single bubble, we are haunted by the constraints of time and choice. We can only live one life. But in the infinite space of the level 1 multiverse, you are living all of them simultaneously. There is a world where you avoided every mistake you ever made. There is a world where you achieved every dream you ever had. These people are not strangers. They are you, separated only by space. Does knowing this make you feel less significant, as if you were just one product on a shelf of millions? Or does it make you feel liberated, knowing that the pressure to be perfect is an illusion because somewhere out there, you already are? The implications of this theory go beyond just personal variations. If the universe is infinite and ergodic, which is a fancy way of saying it eventually explores every possible state, then it must contain everything that is physically allowed by the laws of nature. This is often called the totalitarian principle of physics. Everything that is not forbidden is compulsory. If the laws of physics do not explicitly say no, then the multiverse eventually says Yes. This means that somewhere in the infinite expanse, there is a planet exactly like Earth. But the dinosaurs were never wiped out by the asteroid, and they evolved a civilization. There is a planet made entirely of diamond. There is a volume of space where the atoms have randomly assembled themselves into a floating replica of the 19th century London, complete with people who have false memories of living there. It sounds absurd. Our intuition screams that this is impossible. But we have to remember that our intuition evolved to deal with a very small, very finite world. We deal with probabilities, not certainties. In our world, it's incredibly unlikely that wind will blow sand into the shape of a castle. But if you have an infinite desert and infinite wind, it will happen. In fact, it will happen an infinite number of times. The infinite library of space contains every book that can possibly be written. It contains a book that is full of gibberish. It contains a book that is this script, but with one typo. And it contains the true history of the future of mankind. The only thing that does not exist in the multiverse is a logical contradiction. You cannot have a square circle, but anything else, it is out there. The problem, of course, is that out there is a very lonely place. We know the library exists, but can we ever read the other books? This brings us to the sobering reality of our situation. We have established that the copies are real and that the variations are endless. But we have also established that the distances are mind-numbing. The speed of light is the cosmic speed limit, and it creates a prison wall that we can never breach. This wall is called the particle horizon. Because the universe is only 14 billion years old, light has only had 14 billion years to travel. This draws a sphere around us. Anything outside this sphere is causally disconnected from us. We cannot see it, we cannot signal it, and it cannot affect us. The closest copy of you is 10 to the power of 10 to the power of 29 meters away. But our horizon is only 10 to the power of 26 meters away. Do you see the tragedy of the math? The copies are mathematically guaranteed to exist, but they are also physically guaranteed to be beyond our reach. We are like a person trapped in a small glass room, floating in the middle of a populated ocean. We know there are other ships out there. We know there are other people. But the glass is opaque, and the radio is dead. We are functionally alone, even if we are existentially surrounded. So, is this just a comforting fairy tale we tell ourselves? A story about infinite space to make us feel immortal? If we can never see these copies, is there any difference between far away and imaginary? To convince the skeptics, we need more than just math about infinite space. We need physical evidence. We need to find a fingerprint. We need to find a place where the wall between the worlds cracked, just for a moment, and left a scar that we can see from Earth. And believe it or not, astronomers might have already found it. We have spent the last hour exploring the multiverse as a concept of logic and mathematics. We talked about infinite card decks, repeating patterns and horizons we can never cross. For many people, this is where the journey ends. They file these ideas away under fascinating but unprovable and go back to their daily lives. And it is a fair critique. After all, if these other worlds are separated from us by the speed of light or hidden in abstract dimensions, isn't discussing them just a modern form of theology? Without physical evidence, the multiverse is just a mathematically consistent ghost story. But science does not like ghost stories. It likes data. It likes fingerprints. It likes scars. If we truly live in a chaotic, bubbling foam of universes, and not just a lonely singular bubble, then it is statistically unlikely that we have floated in perfect isolation for 13.8 billion years. Think about a crowded ballroom filled with dancers. Even if the dancers try to stay in their own lanes, eventually, someone is going to bump into someone else. In the cosmic foam model, our bubble is expanding. The bubbles around us are also expanding. Unless the distances between us are perfectly tuned to keep us apart, a collision is not just possible, it is probable. And if two universes crashed into each other, that event would release a cataclysmic amount of energy. It would ring the fabric of space-time like a bell. It would leave a mark. So, Instead of looking for these worlds with a telescope, maybe we should be looking for the wreckage of a cosmic car crash. Astronomers realized that if such a collision happened in the distant past, the evidence would be plastered across the sky, hidden in the faint background glow of the universe. The question is, do we have a camera sensitive enough to see a bruise on the skin of the cosmos? And if we found one, would we be brave enough to admit what it is? To hunt for this evidence, we have to look at the oldest light in existence. It is called the cosmic microwave background, or CMB. If you turn on an old analog television to a channel with no broadcast, about 1% of that static snow is actually radiation left over from the Big Bang. It is the afterglow of the fire that started it all. In 1965, two radio astronomers named Arno Penzias and Robert Wilson accidentally discovered this signal. They were trying to use a giant antenna in New Jersey to listen to mundane radio echoes, but they couldn't get rid of a persistent, annoying hum coming from every direction in the sky. They thought it was pigeon droppings on the antenna. They cleaned it, but the hum remained. They eventually realized they were listening to the scream of the infant universe, a relic from a time when the cosmos was a hot, dense soup of plasma. This light has been traveling for over 13 billion years. As the universe expanded and cooled, that original blinding light stretched out into invisible microwaves. Today, we have mapped this radiation with incredible precision, using satellites like WMAP and Planck. When we plot this data on a map, it looks like a speckled oval of orange and blue patches. The orange spots represent regions that are slightly warmer and denser, where galaxies eventually formed. The blue spots are slightly cooler and emptier. According to the standard model of cosmology, this map should be uniform. The temperature variations should be tiny and random, distributed evenly across the sky like grains of sand on a beach. This uniformity is the bedrock of our understanding of the universe. It tells us that on the grand scale, space is the same everywhere. But what happens when the map shows us something that breaks the rules? What happens when the baby picture of the universe has a giant scar on its face? In 2004, NASA researchers were analyzing the new high-resolution map from the WMAP satellite when they noticed something that shouldn't be there. Down in the southern hemisphere of the sky, in the direction of the constellation Eridanus, there was a blue spot. But it wasn't just a normal blue fluctuation. It was a massive, deep blue hole. This region is known today as the CMB Cold Spot. It is a patch of sky about 5 degrees or 1 billion light years across, which is significantly colder than the surrounding universe. Specifically, it is about 70 microkelvins colder than the average. That sounds like a tiny number to you and me, but in the delicate thermodynamics of the early universe, 70 microkelvins is the difference between a ripple and a tsunami. Statistically, the chance of a spot this large and this cold appearing by random chance in a standard universe is roughly 1 in 50. It is an anomaly. It sticks out like a sore thumb. Imagine looking at a perfectly smooth, calm lake and suddenly seeing a giant, frozen whirlpool in one corner that refuses to melt. That is the cold spot. For years, astronomers tried to wish it away. They thought it might be an error in the satellite's sensors. Maybe the software processed the data wrong. Maybe it was some foreground interference from our own galaxy. But when the European Space Agency launched the even more advanced Planck satellite in 2009, the cold spot was still there, staring back at us with the exact same shape and intensity. It was not a glitch. It was a physical structure woven into the fabric of reality. The question shifted from, is it real, to what monster could possibly create a hole that big? The first instinct of the scientific community was to look for a solution inside our own universe. They proposed that the cold spot was caused by a supervoid. A void is a vast region of space that is relatively empty of galaxies and dark matter. If light from the CMB travels through a giant empty void, it loses energy as it climbs out of the gravitational well, a phenomenon known as the integrated Sachs-Wolf effect. If the void is big enough, the light gets tired, stretches out, and appears colder to our telescopes. It was a sensible, comfortable theory. It suggested that there was just a big empty cavern in the constellation Eridanus. But when astronomers pointed optical telescopes at that region to count the galaxies, the math didn't add up. They did find a void, now called the Eridanus Supervoid, but it wasn't nearly empty enough or big enough to account for the massive temperature drop. To explain the cold spot with a void, the void would have to be impossible. It would have to be a structure so vast that it would challenge the laws of how structure forms in the universe. It would be like finding a canyon on Earth that is deeper than the planet is wide. The supervoid hypothesis was a desperate attempt to keep the solution local. But as the data piled up, the local explanation began to crumble. The hole was too deep. The energy loss was too extreme. If our universe couldn't dig a hole that big on its own, then perhaps the shovel came from the outside. Enter Dr. Laura Mersini-Houghton, a theoretical physicist who proposed a radical solution that fits the data terrifyingly well. She suggested that the cold spot is not a void, it is a bruise. Her hypothesis is based on the idea of the bubble multiverse we discussed earlier. Imagine our universe is a soap bubble floating in a room full of other bubbles. If our bubble drifted too close to another one and they touched, the collision would not necessarily destroy them. Instead, it would push the walls of our universe inward. This impact would release a massive shockwave of gravity and energy, pushing matter away from the point of contact. As the universes bounced off each other and expanded, that contact point would stretch out, leaving a giant, circular region of lower density and temperature. It would look exactly like the cold spot we see today. Mersini-Houghton actually predicted the existence of such anomalies before the data was fully analysed. Her model suggests that the cold spot is the remnant of a cosmic fender bender that happened billions of years ago. If she is right, we are looking at the first physical evidence of a reality beyond our own. We are staring at the imprint of a neighbouring universe that brushed against us in the dark. This changes the cold spot from a statistical curiosity into the most significant object in the history of science. It is a window. If you could fly a spaceship into the centre of the cold spot, would you be closer to the edge of the bubble? Would the veil between the worlds be thinner there? We don't know. But the fact that we have a physical mark on the sky that matches the predictions of the multiverse theory suggests that the glass wall might not be as impenetrable as we thought. And if there is one neighbour that left a bruise, how many invisible neighbours are floating right here, closer than our own skin, disguised by a dimension we cannot see? The collision hypothesis is incredibly seductive because it turns a boring universe into a dynamic battlefield of bubbles. But science is not about what is cool, it is about what is true. So after Laura Mersini-Houghton proposed the idea, the entire cosmological community turned their eyes to the European Space Agency's Planck satellite. Launched in 2009, Planck was designed to create the ultimate, high-definition map of the early universe. It was the gold standard. If the cold spot was just a trick of the light or a mistake by the older WMAP satellite, Planck would wipe it away. But when the data came back in 2013, the cold spot did not vanish. It became sharper. Planck confirmed that the temperature anomaly was statistically significant, reaching a level of roughly 3 sigma. This means there is a 99.7% chance that the feature is real and not random noise. But more importantly, the shape of the spot matched the simulations of a bubble collision. When two spheres intersect, they do not create a square hole or a jagged tear. They create a circle with a specific temperature gradient, getting colder towards the center. This is exactly what Planck saw. The data ruled out many of the alternative explanations involving instrument error or local dust interference. While we cannot say with 100% certainty that this is a bruise, the collision model remains one of the few theories that actually fits the physical evidence without breaking the laws of probability. The implications of this are staggering. If the cold spot is indeed a scar from a collision, it proves that our universe is not an isolated system. It proves that there is a medium outside of our space-time, a higher dimensional space where universes float and crash like ships in a storm. It transforms the multiverse from a mathematical possibility into a physical geography. We have a neighbor. We have touched them. And if we touched them once, billions of years ago, who is to say we aren't bumping into someone else right now? What if the bumping isn't happening at the edge of the universe, but right here, under our noses? This brings us to a critical shift in our perspective. Up until now, we have been talking about parallel worlds as things that are far away. We talked about copies of you living 10 to the power of 29 meters away. We talked about bubbles colliding at the edge of the visible cosmos. In this mental model, the multiverse is just a really, really big map. To get to the other world, you just need a spaceship with infinite fuel and billions of years of travel time. It is a concept of distance, but distance is just one way to be separated from someone. Imagine you are listening to a radio in your car. You are tuned to 99.5 FM, listening to classic rock. Is the jazz station on 100.3 FM far away from you? No. The radio waves for the jazz station are filling the exact same space inside your car as the rock station. They are bouncing off your dashboard and passing through your body at this very second. They are here. You just cannot hear them because they are vibrating on a different frequency. Theoretical physics suggests that reality might be structured exactly like that radio. There could be other universes that are not billions of light years away, but zero distance away. They could be superimposed right on top of us, occupying the same volume of space, but separated by a dimension we cannot perceive. This is the concept of the brain multiverse. It suggests that a parallel version of you could be sitting in your chair right now, reading a different screen, and you would never know they were there. But if they are so close, why don't we bump into them? Why don't we see them? To understand the invisible wall that separates us, we have to solve a mystery that has baffled physicists for a century. Why is gravity so pathetically weak? You probably don't wake up in the morning thinking that gravity is weak. It feels pretty strong when you trip and fall, or when you try to lift a heavy box. But compared to the other fundamental forces of nature, gravity is laughably, embarrassingly feeble. Let me give you a simple experiment you can do in your kitchen. Take a tiny fridge magnet and hold it over a paperclip. The magnet will easily lift the paperclip off the table. Think about the tug of war that is happening there. On one side, you have the entire planet Earth, 6 septillion kilograms of rock and iron, pulling the paperclip down with all its gravitational might. On the other side, you have a tiny piece of magnetized metal pulling it up, and the magnet wins, effortlessly. The electromagnetic force inside that tiny magnet is stronger than the gravitational force of the entire world. Specifically, electromagnetism is about 10 to the power of 40 times stronger than gravity. That is a 1 with 40 zeros. To give you a sense of scale, that is roughly the difference between the weight of a single virus and the weight of the entire visible universe. This creates a huge headache for physicists. In nature, things are usually balanced. Why is gravity the runt of the litter? Why is it so incredibly diluted compared to the other forces like the strong nuclear force or electromagnetism? For decades, this was known as the hierarchy problem. It didn't make sense, but in 1999, 2 physicists named Lisa Randall and Raman Sundaram proposed a solution that changed everything. They suggested that gravity isn't actually weak. It is just as strong as the other forces, but unlike the other forces, it is leaking. Imagine you are watering your garden with a hose, but the water pressure is terrible. You check the hose and find it is full of holes, spraying water out sideways before it reaches the nozzle. Randall and Sundaram suggested that our universe is a leaking hose, and the water escaping from it is gravity. But where is it leaking to? The answer lies in the existence of extra dimensions. We are used to living in 3 dimensions of space: left-right, forward-backward, and up-down. But string theory and its big brother, M theory, require the existence of at least 10 or 11 dimensions to work mathematically. We usually assume these extra dimensions are curled up tightly, too small to see. But Randall and Sundaram propose that some of these dimensions might be large, perhaps infinite, but inaccessible to us. In their model, our entire three-dimensional universe is like a thin membrane, or a brain, floating in a higher dimensional space called the bulk. Think of our universe as a shower curtain hanging in a large bathroom. The bathroom is the bulk. The theory states that the particles that make up our bodies and our light, electrons, quarks, photons, are open strings. Their ends are physically stuck to the shower curtain. They cannot leave the brain. This is why we cannot see the bulk. Light is trapped on the curtain. But gravity is different. According to string theory, the particle that carries gravity, the graviton, is a closed string. It is a loop. It has no loose ends to get stuck to the brain. This means gravity is free to drift away from our universe and float out into the bulk. This explains why gravity feels so weak to us. We are only feeling the tiny fraction of gravity that remains on our slice of the universe, while the rest of it is leaking out into the extra dimensions. This solves the hierarchy problem perfectly. Gravity is strong, but it is diluted by the volume of the higher dimensions. But this solution comes with a haunting implication. If gravity can leave our universe and travel into the bulk, can it also travel from the bulk back to us? And more importantly, is there anything else floating in that bathroom? If we accept the brain world hypothesis, our view of reality shifts from a single bubble to a giant loaf of sliced bread. Our universe is just one slice, but there could be another slice, another brain, floating right next to us, separated by only a millimeter of bulk space. This fourth spatial dimension is a direction you cannot point to, but it is physically there. Imagine you are a two-dimensional ant living on a flat sheet of paper. You can walk forward, backward, left, and right. You have no concept of up. Now imagine I place another sheet of paper parallel to yours, just a fraction of an inch above you. On that second sheet, there is another ant. To you, the first ant. That second ant does not exist. You cannot see him because light travels along the paper. You cannot touch him. He is completely invisible to your reality. But, and this is the crucial part, since gravity can move through the empty space between the sheets, you might be able to feel him. If the other ant is heavy enough, his gravity would pull on your world. You would see strange phantom forces in your universe. You might see stars orbiting around nothing, pulled by the gravity of a dark star on the parallel brain. This model suggests that what we call dark matter, the mysterious invisible substance that makes up 85% of the mass in the universe, might not be matter in our universe at all. It could be the gravitational shadow of ordinary matter living on a parallel brain just next door. We might be sharing our space with an entire shadow civilization that is less than an atom's width away in the fourth dimension. We are alone on our sheet of paper, but the stack is full. And sometimes, the sheets might flap in the cosmic wind and touch. The idea that we are sharing our room with invisible neighbors sounds like something out of a ghost story, but it is actually the leading explanation for the biggest missing person case in the history of science. When astronomers look at the way galaxies spin, they notice something impossible. The stars on the outer edges of a galaxy are moving way too fast. Based on the amount of visible matter, stars, gas and dust, there is simply not enough gravity to hold them in orbit. By all laws of physics, these galaxies should fly apart like a spinning carousel that is moving too fast, but they don't. They hold together perfectly. This implies that there is some massive, invisible glue holding them together, a source of gravity that we cannot see. We call this dark matter. For decades, we have assumed that dark matter is just a cloud of exotic particles floating inside our own universe that, for some reason, refuses to reflect light. We have built billion-dollar detectors deep underground to catch these particles, but so far, we have found absolutely nothing. The detectors are silent. This silence has led physicists to reconsider the brain world hypothesis. What if the reason we cannot find the dark matter particle is that it is not in our universe at all? If there is a parallel brane floating just a millimeter away from us in the fourth dimension, and that brane is filled with its own stars and galaxies, we would not be able to see them. Their light is stuck to their brane, just as our light is stuck to ours. But as we discussed, gravity can jump the gap. The gravity from those shadow stars would cross the bulk and pull on the stars in our galaxy. We would see our stars moving faster, pulled by an invisible hand. We would measure the extra gravity and call it dark matter, completely unaware that we are actually detecting the weight of a parallel world. This leads to a dizzying thought. If the shadow brane is that close, could there be complex structures on it? Could there be a shadow Earth orbiting a shadow sun right here in terms of three-dimensional space, but displaced in the fourth? When you walk through an empty room, are you actually walking through the walls of a shadow city? The physics does not rule it out. We might be ghosting through each other's civilizations at this very moment, separated by a gap smaller than an atom. But if the gap is so small, is it stable? Or is there a danger that the sheets might touch? To wrap your mind around how two solid realities can exist in the same space without crashing into each other, we need to stop thinking about space as a container and start thinking about it as a spectrum. Imagine you are sitting in your living room right now. If you turn on a radio, you can tune into a pop station on 99.5 megahertz. The music fills the room. Now, you turn the dial to 100.3 megahertz and hear classical music. The classical music was already there. It was filling the exact same volume of air as the pop music. The two songs are occupying the same space at the same time, passing through each other without mixing. They don't collide because they are vibrating at different frequencies. In physics, we say they are orthogonal to each other. They exist independently. The brain multiverse suggests that physical reality works on the same principle, but instead of sound waves, we are talking about probability waves of matter. Our entire universe, every atom in your body, every star in the sky, is vibrating at a specific quantum frequency. The parallel brane next door is vibrating at a different one. This is why you don't fall through the floor into the other world. The electrons in your shoes are interacting with the electrons in the floor because they share the same frequency. They are tuned to the same station. But the electrons in the shadow world pass right through you because they are on a different channel. We are walking through a crowded room, but our senses are only tuned to receive one specific broadcast. However, the analogy has a dark side. In radio, sometimes signals drift. Sometimes, if the atmospheric conditions are right, two stations overlap, and you hear a chaotic burst of static where both songs play at once. Does the multiverse have an equivalent to this static? What happens if the two branes, which are floating freely in the higher dimensional bulk, drift too close and actually make physical contact? The theory suggests that this isn't just a glitch that causes static. It is a cataclysm that resets the clock of eternity. In 2001, physicists Paul Steinhardt and Neil Turok proposed a radical new history of our cosmos based on this idea of colliding branes. They called it the ekpyrotic universe, named after the ancient Greek word for conflagration or fire. Their theory challenges the standard idea that the Big Bang was the beginning of time. Standard cosmology says that before the Big Bang, there was nothing. No space, no time, just a singularity that appeared out of nowhere. That has always felt like a cheat. It feels like magic. Steinhardt and Turok offered a more physical explanation. They suggested that the Big Bang was not a beginning, but a collision. Imagine two giant metal plates, two branes, floating in the dark void of the bulk. They are attracted to each other by gravity. Slowly, over billions of years, they drift closer and closer. As they approach, they accelerate. Finally, they slam into each other with unimaginable force. The energy of this collision is dumped into the branes, heating them up instantly to billions of degrees. This heat and energy is what we call the Big Bang. It wasn't a creation from nothing. It was the kinetic energy of the crash being converted into hot plasma. The brains bounce off each other, expand and cool down, allowing stars and galaxies to form. This is the period we are living in now. But eventually the expansion will stop. Gravity will take over, and the brains will be pulled back together for another crash. This implies that our universe is cyclical. We are just one beat in an eternal cosmic rhythm. Bang, expansion, cooling, contraction, bang. It has happened trillions of times before, and it will happen trillions of times again. If this is true, then the history of the universe is not a straight line from birth to death. It is a heartbeat. And if the universe has a heartbeat, does that mean it is alive? This brings us to the strangest and most beautiful theory of all. The idea that the multiverse is not just a machine, but an organism that is evolving. Up until this point, we have looked at the multiverse through the cold, hard lens of mechanical physics. We have talked about colliding sheets of metal, boiling water, and shuffling decks of cards. These metaphors treat the universe as a dead object, a clockwork mechanism that grinds on blindly, governed by rigid mathematical laws. In this view, life, you, me, the trees outside, is just a happy accident. We are mold growing on the gears of the machine, irrelevant to its operation. But what if we have it backwards? What if life is not an accident, but the point? When we look at the complexity of the cosmos, it bears a striking resemblance to something we see in biology. It grows. It has a life cycle. It consumes energy. And, as we are about to see, it might even reproduce. There is a controversial but compelling theory known as cosmological natural selection, proposed by the theoretical physicist Lee Smolin. He suggests that the laws of physics themselves are not set in stone, but are subject to the same evolutionary pressures that shape the birds and the bees. Think about how radical this shift is. In standard physics, the electron has a certain mass because that's just how it is. It is a brute fact. But in biology, nothing is just how it is. A giraffe has a long neck for a reason, because its ancestors with short necks died out. Smolin asks us to apply this logic to the stars. Could it be that our universe has the specific laws it does because it evolved them? Could it be that we are living in the fittest universe, the one that won the competition for survival? To understand this, we first have to look at the problem that convinced Smolin that the universe is rigged. The problem is known as the Finetuning, or the Goldilocks enigma. When physicists measure the fundamental numbers that define our reality, they find something disturbing. The universe seems to be balanced on the edge of a knife. Let's look at the strength of the dark energy that is pushing the universe apart. It is a tiny, specific number. If this number were just a fraction larger, the universe would have expanded so fast that atoms would have been torn apart before they could form stars. If it were a fraction smaller, the universe would have collapsed back into a black hole milliseconds after the Big Bang. The same is true for the strong nuclear force that binds protons together in the nucleus of an atom. If it were 2% stronger, hydrogen would fuse into helium instantly, and there would be no water and no stars like our sun. If it were 2% weaker, nuclei would fall apart and the periodic table would be empty. The list goes on. There are about 20 of these numbers, and every single one of them falls into the incredibly narrow range required for life to exist. The odds of this happening by random chance are effectively zero. It is like throwing a dart from an airplane and hitting a specific grain of sand in the Sahara Desert. So, we are left with two options. Option A. It is a miracle. A creator set the dials to exactly the right numbers to make us. Option B. It is a survivor bias. There are trillions of failed universes with bad numbers, and we are in the one that works. But Lee Smolin offered a third option. Option C. The universe is not lucky. It is adapted. Just as a polar bear is adapted to the cold not by chance but by heritage, our universe is adapted to creating life because it inherited those traits from a parent. But if the universe has a parent, how is it born? And where is the egg? The answer to where the egg lies was formulated in 1992 by the theoretical physicist Lee Smolin in his book, The Life of the Cosmos. Smolin looked at the similarities between the world of biology and the world of physics and realized they were practically mirroring each other. In biology, we have the concept of the genotype and the phenotype. The genotype is the genetic code, the DNA instructions that tell the cells how to build the body. The phenotype is the body itself, the physical animal that has to survive in the forest. Smolin proposed that the universe follows the exact same structure. In his theory of cosmological natural selection, the body is the physical universe we see around us. The galaxies, the vacuum, the light. But what is the DNA? Smolin suggested that the genes of the universe are the fundamental constants of nature. The mass of the proton, the strength of the weak nuclear force, the speed of light. These are not random numbers. They are the genetic code that determines the shape and behavior of the universe. Just as a small change in DNA can turn a wolf into a chihuahua, a small change in these constants can turn a universe filled with stars into a universe filled with diffuse gas. Smolin's radical insight was to apply the logic of Darwinian evolution to these cosmic genes. In Darwin's theory, the key to success is reproduction. An animal that leaves no offspring removes its genes from the gene pool. An animal that leaves many offspring spreads its genes until they dominate the population. Smolin argued that universes must do the same thing. They must reproduce. And for reproduction to drive evolution, the offspring must be similar to the parent, but not identical. There must be slight mutations. If this is true, it means that our universe was not created from scratch. It was born. It has a mother. And somewhere out there, it might be giving birth to children of its own. But if a universe is a giant expanding bubble of space-time, how exactly does it make a baby? What physical mechanism could possibly take a pinch of space-time and grow it into a new reality? To find the reproductive organ of the cosmos, we have to look at the most violent and mysterious objects in the sky. We have to look at black holes. For a long time, we viewed black holes as the trash cans of the universe. A star runs out of fuel, collapses under its own weight, and tears a hole in the fabric of space-time where nothing, not even light, can escape. We saw them as endpoints, places where information goes to be erased, but general relativity suggests a different picture. When a massive star collapses, it squeezes a huge amount of matter into a tiny point called a singularity. At this point, the density becomes infinite and the laws of physics as we know them break down. But the math suggests that the space-time does not just end at the singularity. Instead, it bounces. Think of a rubber sheet. If you push a heavy marble down into the sheet, it stretches the rubber into a deep funnel. If you push hard enough, the funnel might pinch off at the bottom and expand outward into a new bubble on the other side. Smolin suggests that this is exactly what happens. The singularity is not a dead end. It is a seed. The matter and energy that fall into the black hole in our universe do not disappear. They are funneled through an Einstein-Rosen bridge, a wormhole, and erupt out the other side, triggering a Big Bang in a completely new, separate region of space-time. From our perspective, the black hole is a dark, heavy sphere. But from the perspective of an observer inside the black hole, it looks like the beginning of time. It looks like a new universe expanding rapidly from a hot, dense point. This means that every black hole in our galaxy is technically a baby universe in the making. It is growing, expanding, and developing its own structure, completely cut off from us by the event horizon. The event horizon is the shell of the egg. We cannot see inside it, and the baby cannot see out. But the crucial part of Smolin's theory is what happens to the genes during this birth. Does the baby inherit the physics of the parent? If the baby universe were a perfect clone of the parent, there would be no evolution. Everything would stay the same forever. But quantum mechanics introduces an element of randomness. Smolin hypothesizes that when the singularity bounces, The extreme energy fluctuations cause the constants of physics to shift slightly. It is a cosmic mutation. The baby universe might have a proton that is 0.1% heavier than its parent. It might have a force of gravity that is slightly stronger. This small variation creates the pressure of natural selection. Think about it. Some universes will have bad genes. Maybe the mutation makes gravity too weak to form stars. In that universe, the gas just floats around forever. No stars means no black holes. No black holes means no babies. That universe is sterile. It is a genetic dead end. It lives out its life and fades away without passing on its legacy. But other universes will have good genes. They will have laws of physics that are perfectly tuned to turn gas clouds into massive stars, which then collapse into black holes. A universe with these genes is highly fertile. It might produce trillions of black holes, which means it produces trillions of children. Each of those children inherits the star-making genes and perhaps refines them even further. Over billions of generations, the population of the multiverse will be completely dominated by these fertile universes. The bad universes will be rare statistical flukes, while the good universes will be everywhere. This explains the fine-tuning problem without any need for magic. Why are the laws of our universe so perfect for making stars? Because our universe is the product of a long lineage of master breeders. We are not the first iteration of reality. We are the result of aeons of cosmic optimization, designed by trial and error to be a black hole factory. But if the goal of the universe is just to make black holes, where do we fit in? Are we just accidental tourists in a factory that wasn't built for us? This leads to a humbling realization about the nature of life. We like to think that the universe is fine-tuned for us. We look at the sun, the water, and the carbon atoms, and we say, look how perfect this is for human beings. But Smolin's theory suggests that this is a case of mistaken identity. The universe is not fine-tuned for life. It is fine-tuned for black holes. It just so happens that the conditions required to make a black hole are almost identical to the conditions required to make life. To make a black hole, you need massive stars. To get massive stars to form out of gas clouds, you need a way to cool the gas down so it can clump together. It turns out that the most efficient coolant in the cosmos is carbon monoxide. You need heavy elements like carbon and oxygen to act as chemical radiators to help stars condense. So, a fertile universe must produce huge amounts of carbon and oxygen. It must allow for complex chemistry. These are the exact same ingredients needed to build a human being. We are not the purpose of the universe. We are a chemical byproduct of the reproductive system of the cosmos. We are like the moss growing on the bark of a tree. The tree exists to drop acorns and grow more trees, not to support the moss. But the moss thrives anyway because the conditions on the bark are right. Does knowing that you are a side effect make you feel insignificant, or does it make you feel connected? You are made of the same star stuff that the universe uses to build its children. The carbon in your DNA is the same carbon that cools the clouds of the Orion Nebula. We are commensal organisms, riding the wave of a much larger evolutionary process. But there is one wild card in this theory. What if biology isn't just a side effect? What if we are actually part of the mechanism? If we follow the logic of evolution to its limit, we have to ask if nature ever stops innovating. In biological evolution, simple cells eventually teamed up to form complex animals because complex animals were better at survival. Could the same thing happen to universes? Right now, the universe makes black holes through a dumb, brute force method, gravity crushing stars. It is messy and inefficient. Most of the matter in a star is blown away in the explosion. Only a small core becomes a black hole. But what if a universe evolved a more efficient way to reproduce? What if it evolved a tool that could take matter and deliberately compress it into black holes with precision? That tool would look a lot like intelligent life. Think about it. We are already smashing particles together at high energies. Theorists have speculated that a sufficiently advanced civilization could manufacture artificial black holes for energy or computation. If a universe evolves intelligent life, and that life goes on to build billions of artificial black holes, that universe has a massive reproductive advantage. it will have far more children than a universe with only dumb stars. This suggests a dizzying possibility. Maybe we are not just moss. Maybe we are the reproductive cells of the cosmos. Maybe the reason the laws of physics allow for intelligence is that intelligence is the next stage of cosmic evolution. We are the way the universe learns to clone itself. This perspective shifts our role from accidental passengers to essential pilots. We might have a job to do, but before we get too arrogant about our future, we have to look at the one thing that biology cannot control: the flow of time itself. We have explored the evolution of matter, but we still haven't answered why the movie only plays in one direction. Why can't we remember the future? The answer lies in the mirror. The answer to where the egg lies was formulated in 1992 by the theoretical physicist Lee Smolin in his book, The Life of the Cosmos. Smolin looked at the similarities between the world of biology and the world of physics, and realized they were practically mirroring each other. In biology, we have the concept of the genotype and the phenotype. The genotype is the genetic code, the DNA instructions that tell the cells how to build the body. The phenotype is the body itself, the physical animal that has to survive in the forest. Smolin proposed that the universe follows the exact same structure. In his theory of cosmological natural selection, the body is the physical universe we see around us. The galaxies, the vacuum, the light. But what is the DNA? Smolin suggested that the genes of the universe are the fundamental constants of nature. The mass of the proton, the strength of the weak nuclear force, the speed of light. These are not random numbers. They are the genetic code that determines the shape and behavior of the universe. Just as a small change in DNA can turn a wolf into a chihuahua, a small change in these constants can turn a universe filled with stars into a universe filled with diffuse gas. Smolin's radical insight was to apply the logic of Darwinian evolution to these cosmic genes. In Darwin's theory, the key to success is reproduction. An animal that leaves no offspring removes its genes from the gene pool. An animal that leaves many offspring spreads its genes until they dominate the population. Smolin argued that universes must do the same thing. They must reproduce. And for reproduction to drive evolution, the offspring must be similar to the parent, but not identical. There must be slight mutations. If this is true, it means that our universe was not created from scratch. It was born. It has a mother. And somewhere out there, it might be giving birth to children of its own. But if a universe is a giant expanding bubble of space-time, how exactly does it make a baby? What physical mechanism could possibly take a pinch of space-time and grow it into a new reality? To find the reproductive organ of the cosmos, we have to look at the most violent and mysterious objects in the sky. We have to look at black holes. For a long time, we viewed black holes as the trash cans of the universe. A star runs out of fuel, collapses under its own weight, and tears a hole in the fabric of space-time where nothing, not even light, can escape. We saw them as endpoints, places where information goes to be erased. But general relativity suggests a different picture. When a massive star collapses, it squeezes a huge amount of matter into a tiny point called a singularity. At this point, the density becomes infinite and the laws of physics as we know them break down. But the math suggests that the space-time does not just end at the singularity. Instead, it bounces. Think of a rubber sheet. If you push a heavy marble down into the sheet, it stretches the rubber into a deep funnel. If you push hard enough, the funnel might pinch off at the bottom and expand outward into a new bubble on the other side. Smolin suggests that this is exactly what happens. The singularity is not a dead end. It is a seed. The matter and energy that fall into the black hole in our universe do not disappear. They are funneled through an Einstein-Rosen bridge, a wormhole, and erupt out the other side, triggering a Big Bang in a completely new, separate region of space-time. From our perspective, the black hole is a dark, heavy sphere. But from the perspective of an observer inside the black hole, it looks like the beginning of time. It looks like a new universe expanding rapidly from a hot, dense point. This means that every black hole in our galaxy is technically a baby universe in the making. It is growing, expanding, and developing its own structure, completely cut off from us by the event horizon. The event horizon is the shell of the egg. We cannot see inside it, and the baby cannot see out. But the crucial part of Smolin's theory is what happens to the genes during this birth. Does the baby inherit the physics of the parent? If the baby universe were a perfect clone of the parent, there would be no evolution. Everything would stay the same forever. But quantum mechanics introduces an element of randomness. Smolin hypothesizes that when the singularity bounces, the extreme energy fluctuations cause the constants of physics to shift slightly. It is a cosmic mutation. The baby universe might have a proton that is 0.1% heavier than its parent. It might have a force of gravity that is slightly stronger. This small variation creates the pressure of natural selection. Think about it. Some universes will have bad genes. Maybe the mutation makes gravity too weak to form stars. In that universe, the gas just floats around forever. No stars means no black holes. No black holes means no babies. That universe is sterile. It is a genetic dead end. It lives out its life and fades away without passing on its legacy. But other universes will have good genes. They will have laws of physics that are perfectly tuned to turn gas clouds into massive stars, which then collapse into black holes. A universe with these genes is highly fertile. It might produce trillions of black holes, which means it produces trillions of children. Each of those children inherits the star-making genes, and perhaps refines them even further. Over billions of generations, the population of the multiverse will be completely dominated by these fertile universes. The bad universes will be rare statistical flukes, while the good universes will be everywhere. This explains the fine-tuning problem without any need for magic. Why are the laws of our universe so perfect for making stars? Because our universe is the product of a long lineage of master breeders. We are not the first iteration of reality. We are the result of aeons of cosmic optimization, designed by trial and error to be a black hole factory. But if the goal of the universe is just to make black holes, where do we fit in? Are we just accidental tourists in a factory that wasn't built for us? This leads to a humbling realization about the nature of life. We like to think that the universe is fine-tuned for us. We look at the sun, the water, and the carbon atoms, and we say, look how perfect this is for human beings. But Smolin's theory suggests that this is a case of mistaken identity. The universe is not fine-tuned for life, it is fine-tuned for black holes. It just so happens that the conditions required to make a black hole are almost identical to the conditions required to make life. To make a black hole, you need massive stars. To get massive stars to form out of gas clouds, you need a way to cool the gas down so it can clump together. It turns out that the most efficient coolant in the cosmos is carbon monoxide. You need heavy elements like carbon and oxygen to act as chemical radiators to help stars condense. So, a fertile universe must produce huge amounts of carbon and oxygen. It must allow for complex chemistry. These are the exact same ingredients needed to build a human being. We are not the purpose of the universe. We are a chemical byproduct of the reproductive system of the cosmos. We are like the moss growing on the bark of a tree. The tree exists to drop acorns and grow more trees, not to support the moss. But the moss thrives anyway because the conditions on the bark are right. Does knowing that you are a side effect make you feel insignificant? Or does it make you feel connected? You are made of the same star stuff that the universe uses to build its children. The carbon in your DNA is the same carbon that cools the clouds of the Orion Nebula. We are commensal organisms, riding the wave of a much larger evolutionary process. But there is one wild card in this theory. What if biology isn't just a side effect? What if we are actually part of the mechanism? If we follow the logic of evolution to its limit, we have to ask if nature ever stops innovating. In biological evolution, simple cells eventually teamed up to form complex animals because complex animals were better at survival. Could the same thing happen to universes? Right now, the universe makes black holes through a dumb, brute force method, gravity crushing stars. It is messy and inefficient. Most of the matter in a star is blown away in the explosion. Only a small core becomes a black hole. But what if a universe evolved a more efficient way to reproduce? What if it evolved a tool that could take matter and deliberately compress it into black holes with precision? That tool would look a lot like intelligent life. Think about it. We are already smashing particles together at high energies. Theorists have speculated that a sufficiently advanced civilization could manufacture artificial black holes for energy or computation. If a universe evolves intelligent life, and that life goes on to build billions of artificial black holes, that universe has a massive reproductive advantage. It will have far more children than a universe with only dumb stars. This suggests a dizzying possibility. Maybe we are not just moss. Maybe we are the reproductive cells of the cosmos. Maybe the reason the laws of physics allow for intelligence is that intelligence is the next stage of cosmic evolution. We are the way the universe learns to clone itself. This perspective shifts our role from accidental passengers to essential pilots. We might have a job to do. But before we get too arrogant about our future, we have to look at the one thing that biology cannot control: the flow of time itself. We have explored the evolution of matter, but we still haven't answered why the movie only plays in one direction. Why can't we remember the future? The answer lies in the mirror. We have spent the last few hours dissecting the architecture of space. We have looked at space as a bubbling foam, as a deck of cards, as a vibrating string, and even as a biological organism. In all these models, we treated the universe as a place, a geography that we inhabit. But there is another axis to our reality that is far more personal and far more terrifying than space. I am talking about time. You can stand still in space. You can choose to sit in your chair or walk to the door. You have freedom of movement in 3 dimensions, but you cannot stand still in time. You are being dragged forward at the relentless speed of 1 second per second, towards a future you cannot see, away from a past you cannot return to. This creates a fundamental anxiety in the human experience. We feel trapped in a flow. But why does this flow exist? If we look at the universe as a giant block of space-time, as Einstein suggested, then the past, present, and future all exist simultaneously. So why do we only experience the now? Why can I remember the sandwich I ate yesterday, but I cannot remember the sandwich I will eat tomorrow? It seems like a silly question, but to a physicist, it is a nightmare. In the equations of relativity, there is no distinction between the past and the future. They are just coordinates, like left and right. There is nothing in the math that says time must flow forward. Yet, in our lives, the arrow of time is absolute. We are born, we age, and we fade away. We never unage. We never see a shattered glass assemble itself. This disconnect between the timeless laws of physics and the time-bound nature of our lives suggests that we are missing a huge piece of the puzzle. Is it possible that our perception of time is just a local illusion? And if time is an illusion, could there be a place where it runs backward? To answer this, we have to look at the one law that forces the arrow to point forward and ask if that arrow can ever flip. To understand why time has a direction, we have to look at the concept of messiness, or what physicists call entropy. Imagine you have a pristine, organized library where every book is alphabetized. This is a state of low entropy. Now, imagine an earthquake hits. The books fall off the shelves into a chaotic pile. This is a state of high entropy. It is very easy to go from the organized shelves to the messy pile. Gravity and chance will do it for you. But it is statistically impossible for an earthquake to shake a messy pile of books back into perfect alphabetical order. This is the second law of thermodynamics. It states that in a closed system, disorder always increases. Things break, rot, and cool down. They never spontaneously fix, bloom, or heat up. This increase in disorder is what we perceive as the flow of time. The reason you can distinguish yesterday from tomorrow is that tomorrow is messier than yesterday. The universe started in a state of incredible order at the Big Bang, and has been sliding towards chaos ever since. We are surfing on that wave of disintegration. But here is the dirty secret that textbooks often gloss over. The fundamental laws of motion, Newton's laws, Schrödinger's equation, Maxwell's equations, do not care about entropy. They are time symmetric. This means that if you filmed a video of 2 billiard balls colliding and played it backward, the backward video would obey the laws of physics perfectly. At the microscopic level, there is no arrow of time. An atom does not know the difference between the past and the future. So, if the building blocks of reality are time neutral, why is the building itself time dependent? Why does the movie of the universe only play in one direction? This suggests that the arrow of time is not a law, but a condition. It exists because the universe started in a specific state. But this raises a massive problem. If the universe started in a state of perfect order, where did the stuff that makes up the order come from? And why does the universe look so lopsided? This leads us to the mystery of the missing half of creation. When we talk about the Big Bang, we imagine a massive explosion of energy creating all the matter we see today. But according to the standard model of particle physics, energy cannot just turn into matter. It has to turn into matter and antimatter in equal amounts. For every negatively charged electron created, there must be a positively charged positron. For every proton, an antiproton. Nature insists on balance. This means that the early universe should have been filled with a 50-50 mix of matter and antimatter. But there is a catch. When matter and antimatter touch, they annihilate. They turn back into pure energy. So if the Big Bang produced equal amounts of both, they should have instantly destroyed each other, leaving nothing behind but a bath of dull radiation. There should be no stars, no galaxies, and certainly no humans. The universe should be empty. But look around you. You are here. The chair is here. The stars are here. We live in a universe made almost entirely of matter. We can find tiny traces of antimatter in cosmic rays or particle accelerators, but we have never found an antimatter galaxy or an antimatter star. Somehow, the Great Annihilation failed. Somehow, a huge chunk of matter survived, and all the antimatter vanished. Physicists call this the baryon asymmetry problem. It is one of the biggest embarrassments in science. Did the universe make a mistake? Did the laws of physics change for a few seconds to let matter win? For decades, scientists have been searching for a violation of symmetry that would explain this imbalance, but they haven't found anything strong enough to account for the entire cosmos. It feels like someone stole half the universe. But what if it wasn't stolen? What if it is still there, but hiding in a place we never thought to look? What if the antimatter is hiding in the past? In 2014, a British physicist named Julian Barbour, along with his colleagues, proposed a radical new model that solves the mystery of time and the mystery of the missing antimatter in one stroke. It is called the Janus point theory, named after the ancient Roman god Janus, who had two faces, one looking forward and one looking backward. Barbour suggests that we have been looking at the Big Bang all wrong. We usually picture the Big Bang as the start of the timeline, like the firing of a starting gun. Everything moves away from it into the future. But Barbour argues that the Big Bang was not a beginning. It was a midpoint. It was a bridge. Imagine an hourglass lying on its side. The sand flows from one bulb, squeezes through the narrow neck, and flows into the other bulb. In this metaphor, the narrow neck is the Big Bang, a moment of maximum density and order. The sand is the matter of the universe. Barbour's math shows that when a system of particles collapses into a dense cluster and then expands, it naturally splits into two distinct flows moving in opposite directions away from the center. In our bulb of the hourglass, time flows forward as the universe expands. Entropy increases, galaxies form, and we grow older. But on the other side of the neck, there is another bulb, another universe. In that universe, time also flows away from the center. But relative to us, it is moving into the past. This effectively creates two arrows of time pointing in opposite directions from a shared origin. The reason we don't see the antimatter is that it mostly went into the other bulb. The symmetry of the universe is restored not by finding the missing half here, but by realizing that here is only half the picture. The universe is a butterfly with two wings, and we have spent all of history staring at only one. This mirror universe is not a chaotic wasteland. The laws of physics there are exactly the same as ours. It has gravity, electromagnetism, and light. It likely has its own stars, its own planets, and perhaps its own observers. But the relationship between our world and theirs is mind-bending. From their perspective, their time is flowing forward. They remember their past, which is closer to the Big Bang, and they move toward their future, which is further away. They break eggs and make omelets. But if you could stand in our universe and look at theirs through a magical telescope, everything would look reversed. You would see them aging backward. You would see their universe contracting from a dark void into a bright singularity. You would see broken cups leaping off the floor and sealing themselves. To them, we are the ones running backward. We are the mirror world. This model implies that the Big Bang was not a unique explosion, but a gateway that continually pumps existence into two divergent streams. It is the ultimate realization of Newton's symmetry. For every action, there is an equal and opposite reaction. For our entire history of time, there is an equal and opposite anti-history. Does this other universe contain a Benjamin Button version of you? Probably not. The two worlds separated 13.8 billion years ago. The chaotic shuffling of atoms means that the specific details would be different. It is not a perfect reflection of events, but a reflection of structure. It is a world where the sun rises in what we call the West, made of anti-hydrogen and anti-helium. But the most haunting part is that we can never visit it. To reach it, we would have to travel back in time through the crushing density of the Big Bang, and out the other side. We are physically barred from the other wing of the butterfly. We are drifted apart by the very flow of time that gives us life. But if physics can describe a structure that encompasses all of time, both past and future, does that mean the structure itself is timeless? The existence of a mirror universe flowing backward in time sounds like the perfect setup for a science fiction story where the hero travels to the other side to meet their anti-self. But in the cold reality of physics, such a meeting is strictly forbidden by the architecture of the cosmos. The barrier between us is not just a wall of distance or a difference in vibration. It is a barrier of causality. To reach the mirror world, you would have to travel backwards through time, past the formation of the Earth, past the lighting of the first stars, all the way into the crushing inferno of the Big Bang singularity. Even if you built a ship capable of withstanding the heat, the journey would be conceptually impossible because at the Janus point, the very definition of forward and backward breaks down. It is a singularity where the arrow of time dissolves. But let us imagine for a second that you could bypass the Big Bang. Let us imagine you found a wormhole that acted as a tunnel directly connecting our timeline to the mirror timeline. What would happen if you stepped through and shook hands with your mirror self? The result would be the most violent event you can possibly imagine. Remember, the mirror world is dominated by antimatter. The atoms in your body are made of protons and electrons. The atoms in your twin's body are made of antiprotons and positrons. When matter and antimatter come into contact, they do not just bounce off each other. They completely and instantly convert their mass into pure energy. According to Einstein's famous equation, E equals mc squared. Because the speed of light is so huge, a tiny amount of mass creates a monstrous amount of energy. A handshake between you and your anti-self would release an explosion roughly equivalent to thousands of nuclear weapons detonating at once. The two of you would instantly vanish from existence, transformed into a blinding flash of gamma rays. This suggests that the separation of our worlds is not a tragedy, but a safety feature. The universe keeps the two wings of the butterfly apart because their union means mutual destruction. This isolation leads to a profound sense of loneliness. We know the other half is there. We know that mathematically they complete the equation. They hold the missing balance of the cosmos. But we are forever destined to drift apart, carried away by opposite currents of entropy. We are like two ships starting back to back and sailing endlessly away from each other into the dark. But if we zoom out far enough, past the currents and the ships, does the ocean itself ever move? Or is the movement of time just another trick played by our limited perspective? If we accept the Janus point theory, where the past and future are just directions leading away from a center, we are forced to reconsider the nature of time itself. In our daily lives, time feels like a river. It flows. We are carried along by the current, experiencing one moment after another. We feel that the past is gone and the future is not yet real. But to a physicist using the equations of general relativity, this flow is an illusion. In 1915, Albert Einstein revolutionized our understanding of reality by combining space and time into a single, four-dimensional object called space-time. In this model, time is not a process. It is a dimension, exactly like length, width, or height. Think of a loaf of bread. You can slice the bread into individual pieces. Each slice represents a moment of time, a snapshot of the universe at a specific instant. But the loaf itself exists all at once. The beginning of the loaf, the Big Bang, and the end of the loaf are physically connected and equally real. This is known as the block universe theory. In the block universe, nothing actually happens. The entire history of the cosmos, from the Big Bang to the final fade out, is a static, frozen structure. It is a crystal of events. Your birth, your first kiss, and your final day are all etched into this crystal at different coordinates. They exist simultaneously. The reason you feel like you are moving through time is that your consciousness is crawling along the timeline like a needle on a record player. The record is already finished. The song is already pressed into the vinyl, but as the needle hits the grooves, you experience the music as a sequence of notes. If you lift the needle, the music stops for you, but the song remains on the disc. This perspective suggests that the mirror universe and our universe are just two halves of the same static object. We are the top half of the hourglass. They are the bottom half. Both halves exist in eternal, frozen balance. Does this idea make you feel trapped, knowing that the script is already written? Or does it give you peace? If the block universe is real, it means that nothing is ever truly lost. The moments of joy you experienced in the past are not gone. They are still there, fixed in the amber of space-time, existing forever at their specific coordinates. The universe does not delete its history, it just builds more structure. But what is the structure made of? We have talked about atoms, strings, brains, and time. But what lies beneath the basement of reality? We have now peeled back almost every layer of the cosmic onion. We started with the biological illusion of choice. We went down to the quantum level of atoms. We zoomed out to the foam of the multiverse. We looked at the hidden dimensions of gravity. We explored the evolutionary biology of black holes. And finally, we looked at the frozen crystal of time itself. But there is one question left. A question so deep that it stops being physics and starts being metaphysics. What is the stuff? When we ask what a chair is made of, we say wood. When we ask what wood is made of, we say molecules. Molecules are made of atoms. Atoms are made of subatomic particles like electrons and protons. Protons are made of quarks. But what are quarks made of? If you look at the standard model of particle physics, a quark is described as an excitation in a quantum field. But what is a field? A field is a mathematical value assigned to every point in space. Do you see what just happened? We started with a solid chair and we ended up with a list of numbers. We chased the stuff of reality all the way to the bottom, and the stuff disappeared. We found that the bedrock of the universe is not a solid material, but a set of mathematical properties. An electron is not a tiny ball, it is a collection of values: mass, charge, and spin. If you take away those numbers, there is nothing left. There is no electronness underneath the math. The electron is the math. This realization leads to a concept that might be the ultimate explanation for why the multiverse exists. It suggests that the distinction between the physical world and the world of mathematics is a lie. We usually think of math as a tool we invented to describe the world, like a language. We use numbers to count apples, but the numbers aren't the apples. But what if we are wrong? What if the numbers are the apples? What if the universe is not described by math, but is actually made of math? This radical idea is the brainchild of the cosmologist Max Tegmark, and he calls it the mathematical universe hypothesis. It is the final, fourth level of the multiverse hierarchy, and it encompasses all the others. The logic is surprisingly simple. If physics keeps getting more and more abstract as we go deeper, eventually we have to hit a layer that is purely mathematical. Tegmark argues that our physical reality is a mathematical structure. Think about a video game. When you play a game, you see trees, cars, and people. You hear sounds. You feel the rush of adrenaline. But what is the game really? If you look at the hard drive, there are no trees inside. There is only code. There are only sequences of zeros and ones. The physicality of the game world is an emergent property of the information processing. The code contains the rules that simulate gravity, light, and collision. To a character living inside the game, the tree feels solid. But to the programmer, the tree is just a function. Tegmark suggests that our universe is exactly like that, but without the computer. In math, complex structures exist simply because they are logically consistent. You don't need a computer to make the number pi real. Pi exists, whether you calculate it or not. The ratio of a circle's circumference to its diameter is a timeless truth. It existed before the Big Bang, and it will exist after the stars fade. If mathematical truths exist independently of time and space, and if our universe is just a very complex mathematical structure, then our universe exists necessarily and eternally. It doesn't need a creator to boot it up. It exists in the same way that a triangle exists. It is a feature of logic itself. But here is the part that blows the doors off the multiverse. The structure that describes our universe, with our specific speed of light and our specific gravity, is just one of an infinite number of possible mathematical structures. Logic allows for other structures. It allows for universes with different numbers, different geometries, and different rules. If the math for those universes is consistent, do they exist too? The answer, according to the mathematical universe hypothesis, is a resounding yes. This leads to the most expansive definition of reality possible. It implies that every mathematical structure that does not contain a logical contradiction exists physically. This is often called Platonic realism. The ancient Greek philosopher Plato believed that the perfect forms of things, the perfect circle, the perfect triangle, existed in a higher realm of abstract truth. Tegmark says that we are living inside one of those forms. This means that existence is not a privilege restricted to our specific bubble. Existence is the default state of logic. If a universe can be defined, it is real. There is a mathematical structure that describes a universe with 6 dimensions of space. That universe exists. There is a structure that describes a universe where time flows in a circle. That universe exists. There is a structure that describes a universe completely empty of matter, consisting only of twisting geometric shapes. It exists. This is the level 4 multiverse. It contains the level 1 copies, the level 2 bubbles, and the level 3 quantum branches. It contains everything. The only thing that does not exist is the impossible. You cannot have a universe where 1 + 1 = 3, because that is a contradiction. But anything else goes. This removes the question of why? Why these laws? Why this gravity? The answer is that there is no why. We are just observing one specific address in the infinite neighborhood of mathematics. We are exploring one particular fractal in an infinite set. We are here because this structure supports self-aware substructures called humans. In other structures, there are other beings asking the same question. This implies that reality is not a rare, fragile spark in the dark. It is an absolute, unbreakable infinite. It implies that nothing can ever truly cease to be, because a mathematical truth cannot be destroyed. You are a part of that truth. Does knowing that you are built of eternal logic make you feel cold, or does it make you feel indestructible? To visualize the sheer magnitude of a level 4 multiverse, we have to borrow a metaphor from the Argentine writer Jorge Luis Borges. In his famous story, The Library of Babel, he imagined a library that contained every possible book that could be written. Most of the books were pure nonsense, random strings of letters. But if you searched long enough, you would find the cure for cancer. You would find the true history of the future. You would find a book that explained the meaning of life, and another book that refuted it. Max Tegmark's mathematical universe is the physical version of that library. It does not just contain books, it contains realities. If a universe can be described by a set of non-contradictory equations, it is on the shelf. This means that the diversity of existence is bounded only by logic itself. We often wonder if fictional worlds could be real. We ask, could a world like Star Wars exist? In a standard universe, the answer is no, because the Force violates our laws of physics. But in the level 4 multiverse, the question changes. We ask, is there a mathematical structure that allows for a force field manipulation telekinesis? If the math holds up, if you can write the equation without creating a paradox, then that universe is out there. It might not be Star Wars exactly, but it would be a reality indistinguishable from it to the people living inside. This concept erases the line between the possible and the actual. In our limited human view, we divide the world into things that exist and things that are just ideas. But in the eyes of the mathematical cosmos, an idea is a thing. A possibility is just a reality that you are not currently visiting. This abundance can be overwhelming. It suggests that there is no such thing as fiction. Every story you have ever imagined, every dream you have ever had, is just a distorted glimpse of a distant mathematical structure. This leads to a question that changes how you view your own mind. Are you inventing these stories, or are you just tuning into them? When a writer creates a world, are they building it from scratch, or are they discovering a coordinate in the library that was already there? The level 4 multiverse implies that creativity is actually a form of exploration. We are not creators. We are tourists in a landscape of infinite truth. But if everything exists, does that make our specific reality less special? If there are infinite versions of you, does the one sitting in the chair right now matter at all? This is where physics meets therapy. When we are faced with the idea of infinite copies and infinite variations, our first instinct is often a feeling of devaluation. We think, if there are a billion versions of me, then I am just a cheap commodity. I am replaceable. We feel like a single grain of sand on an endless beach. But there is a different way to look at the math. A way that transforms this cosmic scale into a source of profound comfort. Think about the nature of regret. Regret is the pain we feel when we think we have lost something. We mourn the path not taken. We mourn the mistake that cost us a relationship or a career. We suffer because we believe that the good outcome was destroyed and replaced by the bad outcome. But the multiverse theory tells us that this belief is a lie. Nothing is ever destroyed. The good outcome exists. The version of you who made the right choice is alive and well, enjoying the fruits of that decision at a different coordinate in the mathematical structure. This means that your failures are not absolute. They are local. You are currently experiencing the error coordinate, but the success coordinate is just as real. This realization lifts the crushing weight of what if off your shoulders. You do not have to carry the burden of all the potential lives you didn't live, because you are living them. You are simply focused on this specific track right now. It allows you to look at your life not as a test you can fail, but as a unique pathway through the maze. In a video game, you might play a level perfectly, or you might play a chaotic run where you crash into every wall. Both runs are part of the game. Both are valid experiences. You are currently playing the crash run, and that is okay. It is a unique story that adds to the richness of the total data. The universe does not judge you for being in the messy timeline. The universe contains all timelines with equal validity. So, why do we feel so much pressure to be perfect? Why do we torture ourselves with standards of success that are statistically guaranteed to be met by someone else? Maybe the point of your life isn't to be the best version of you. Maybe the point is simply to witness this specific version, with all its flaws and scars, because no one else in the infinite library can see the world exactly through your eyes. This line of thinking brings us to a philosophy known as optimistic nihilism. Nihilism is usually seen as a dark, depressing idea. The belief that life has no inherent meaning, that the universe doesn't care about us, and that we are accidental, biological scum on a random rock. And scientifically, that is mostly true. As we have seen, the universe is a machine for making black holes, not humans. We are not the protagonists of the story, but optimistic nihilism takes this fact and flips it. If the universe has no inherent meaning, that means it has no inherent demands. You were not created to fulfill a destiny. You were not placed here to pass a test. You are not a cog in a divine plan that will punish you if you wiggle the wrong way. The universe is indifferent, and in that indifference, we find absolute freedom. If the script isn't written for you, you get to write it yourself. You are the only entity in your immediate vicinity that has the power to generate meaning. If you decide that the most important thing in the cosmos is kindness, or art, or exploring the stars, or simply eating a good meal with friends, then that is the meaning of life. The universe cannot contradict you. It is too busy expanding. This makes you the architect of your own value. In a level 4 multiverse where everything is possible, the only thing that distinguishes one reality from another is the subjective experience of the observer. You are the lens that brings the math into focus. Without you, the equations are just static symbols in the dark. With you, they become pain, joy, color, and music. You are the mechanism by which the abstract becomes concrete. This is not a demotion, it is a promotion. You have graduated from being a servant of fate to being a creator of context. So, the next time you look up at the stars and feel small, remember that the stars are just nuclear furnaces. They are big, but they are stupid. You are small, but you are the one doing the looking. You are the one feeling the awe. Doesn't that make you the giant? To fully embrace this freedom, we need to dissolve the barrier between us and the universe. We often talk about the universe as if it is a room we entered, or a foreign country we are visiting. We say, I am in the universe. But the astrophysicist, Neil deGrasse Tyson, following in the footsteps of Carl Sagan, reminds us of a biological fact that corrects this grammar. We are not in the universe. We are of the universe. The atoms in your right hand were forged in the heart of a dying star. The atoms in your left hand might have come from a different star. You are literally made of stardust that has spent billions of years assembling itself into a form that can stand up and look back at the sky. You are the universe waking up. You are the way the cosmos knows itself. In the context of the multiverse, this connection becomes even deeper. If reality is a giant mathematical symphony, you're not just a listener in the audience, you are the music. Every thought you have, every heartbeat, every movement is a vibration in the quantum fields that span eternity. You are a localized ripple in the infinite ocean of structure. This means you are never truly alone. The isolation we spoke of earlier, the particle horizons, the brains, the light years, is an illusion of perspective. Underneath the separation, we are all made of the same fundamental fields. We are all expressions of the same underlying math. The version of you in the parallel world is not a stranger. They are another note in the same chord. The alien civilization in the Cold Spot universe is another instrument in the same orchestra. We are all playing together in a massive, timeless performance. Most of the players are too far away to hear, but we share the same stage. This perspective shifts the feeling of cosmic horror into cosmic awe. The vastness is not there to crush you. It is there to accommodate the sheer scale of the song. You have a solo to play. It is a short solo, maybe 80 or 90 years long, but it is yours. And because the universe is a block, once you play it, that melody is recorded in the crystal of space-time forever. It will never be erased. The question is, what kind of song do you want to play? We have reached the end of our journey through the rabbit hole. We started with a simple question about choices and ended up tearing apart the fabric of reality to find the infinite machinery underneath. We have seen that the world is stranger, larger, and more crowded than our ancestors could have ever dared to imagine. You might walk away from this feeling dizzy. You might look at your reflection in the mirror and see the blur of the quantum fan. You might look at the corner of your room and wonder if a shadow universe is hiding in the gravity. That feeling of vertigo is good. It means you are paying attention. It means you have woken up from the sleepwalk of daily life. Most people live their entire lives without ever questioning the solidity of the ground beneath their feet. They assume that what they see is all there is. But you now know the secret. You know that the walls are thin. You know that you are a multi-dimensional traveler, a child of black holes, and a living mathematical proof. The trap of the universe is real. We are bound by physics, limited by time, and surrounded by silence. But we have the power to decorate the cage. We have the power to fill the silence with our curiosity. So, do not close your eyes. Look for the glitches. Look for the beauty in the chaos. And remember, in a universe where everything is possible, the fact that you exist exactly as you are, right here, right now, is the greatest statistical miracle of all. You are the one possibility that became you. So go out there and live a life worth repeating. Because in the infinite shuffle of the cosmic deck, you might just have to do it all over again. Good luck, and thank you for watching.